everyone, today we are continuing on with our rational functions, looking at lesson 13.2 on page 171. So today we're going to talk a lot about different shortcuts and being able to graph and looking at different types of asymptotes, horizontal, vertical, and oblique. So we've talked a lot about the parameters in the last lesson about our rational function. And we've talked a lot about being able to look at our vertical asymptotes that come from looking at the denominator of our function. So we know here if we set the denominator equal to 0, we would have x squared equals 4. So x equals plus or minus 2 would be our two vertical asymptotes. The numerator here, however, has an x in it as well, which is totally fine. What this is going to allow us to help find is our x-intercept, or our real 0 here. So in that case, it's actually going to be at -5 would be our 0. So -5, 0 would be an x-intercept. Okay. So from here, we're looking to kind of compare what's going on with the horizontal asymptotes based on the functions. So notice here in both g of x and h of x, the degree of the numerator is less than the degree of the denominator, because the degree of the numerator here is 1, the degree of the denominator is 2. Here it's 2, here it's 4. So if we compare these two graphs to each other, g of x and h of x, what we notice here is we have a horizontal asymptote at y equals 0. Now notice with the horizontal asymptotes, unlike vertical asymptotes, it deals with the end behavior. So even though we have a value here at 0, that's okay, because our end behavior follows our horizontal asymptote, which again is at this time at 0. And if we look at the other example here, we also have, again, a horizontal asymptote at 0, because our end behavior as we go to negative infinity and as we go to positive infinity gets really, really close to 0. So what we can say about both of these graphs back in our notes is that if the degree of the denominator is greater than the degree of the numerator, so the degree of the denominator is bigger, what's going to happen is your horizontal asymptote is going to be at y equals 0 each time. Okay? And we could test this out by looking at our own example as well. Now, for number 3, we have u of x and we have v of x. Okay, so going back to our graphs here, we look at u of x and v of x. The degrees are the same. This is both to the first, this is both to the second. So what we're noticing here is this time the degree, or the horizontal asymptote, is at y equals 6 as we look at our end behavior for u of x, and for v of x, our horizontal asymptote ends up being at 1, what we're approaching horizontally. Again, we're looking at the end behavior here and over here. So what we're seeing is that if we reduce the leading coefficients, so 6 divided by 1, that was our horizontal asymptote. It was at y equals 6. And then here, if we reduce this, we ended up having one that was at 1, because the degree of the coefficients 2 divided by 2 was 1. So what we're seeing here is if the degrees are equal in the numerator versus the denominator, what we see is that the horizontal asymptote is at the ratio of the leading coefficients. So it would be whatever your leading coefficient is on the top, whatever your leading coefficient is on the bottom, whatever that reduces to be is your horizontal asymptote. Okay. Now, when the degree of the numerator is bigger, in general, it goes to infinity. We don't have a horizontal asymptote. We will talk later on in the lesson when the degree of the numerator is bigger than the degree of the denominator by 1, then we're going to have a special case situation, and we'll talk about that later in the lesson. Okay. So as we keep moving on then, looking at each of these pieces, we have here that we have this information, right? We have this that we've been talking about. So some important things that you're definitely going to want to have jotted down is what we were talking about before. Which degree being bigger, what's going to happen, where your vertical asymptotes are occurring, which again is hopefully kind of old news by now. It's where your denominator equals 0. And then where the x-intercepts are the solutions, that's where your numerator is equal to 0. So this is the really important stuff to get jotted down. If you have not already, I would highly recommend pausing the video and doing that. Okay. Now, moving on from there, we want to talk about being able to sketch these graphs. So imagine you did not have your graphing calculator or Desmos to look at. How would we do this? Well, first and foremost, you're going to want to look at your important pieces. Find your intercepts if they exist, find your horizontal asymptotes if they exist, find the vertical asymptotes if they exist, determine your end behavior based on those asymptotes, and then kind of being able to see all of these pieces testing some intervals. So notice here in the graph sample that they gave, they found the y-intercept. They found the 0 by setting the numerator equal to 0. There was only 1. They found the 2 vertical asymptotes. And then in the picture, which you'll see on your graph here at the bottom of page 172, they plotted those points, and from there they tested a point on each of these 3 regions to see, okay, where'd my graph be below the x-axis or above the x-axis? So kind of using those vertical asymptotes and your zeros as testing intervals, and that's what they were doing right here, was right above that was testing different pieces where the vertical asymptotes and the zeros are at to see if it was positive or negative to sketch, okay? So on the top of page 173, we see these graphs here, and a couple of things we want to do is try graphing these pieces of information. Now, the denominator is, we're going to want to start this by factoring it and looking at what we have here to be able to look at our vertical asymptotes, because right now we have a vertical asymptote at x equals 5, and we have a vertical asymptote at x equals -3. So we're going to want to definitely plot those on our graph first, and we're going to want to sketch these in. The other thing that we see here is that we have a 0 at x equals 0. So we're going to want to make sure we plot that as well, and in this case, that'll also end up being our y-intercept, is because if we plug in 0 for our x values, it would also come out to be 0, which makes sense in this case. Now, which we may want to plot that just so we don't forget about it in the future. Oops. So x-intercept at 0, 0. So finally, we need to pick some points to test here in order to decide, okay, like, is my graph above, is it below? So if we just pick some of these values, for instance, -6 would be this piece of the graph. So we would plug in -6 for our x value. So I'm going to use my store button to help me out here. And then we have x divided by x squared minus 2x minus 15. And we'll see that this ends up being a negative value, so we know it's below the x-axis. So our end behavior here, probably below. And if we look at the horizontal asymptotes here, the degree of the numerator was bigger than was less than the degree of the denominator. So we know we have a horizontal asymptote at y equals 0. So when we follow along here, we're going to have a graph like so. And if we test on the region here, if we test, for instance, maybe -2, we're now going to store as x, we can check this out and see that this is going to end up being positive. A number on this interval here, let's say 2, if we store that as x and test this out, we'll see that that's negative. So we're going to probably have something with an end behavior like so along here. And then finally, if we test a number on this other interval here, let's say +6, because we know it's on the right side of our vertical asymptote, we would see that we have a positive value. So more than likely our graph is looking something like this, still following along that horizontal asymptote though. Okay, so there's a sketch of our graph. Now in the next example, notice here a couple of things. We have vertical asymptotes this time at 2 and -2, because if we look at our denominator, we would have +2 and -2. So we have these vertical asymptotes in here. Our numerator, if we set this equal to 0, we would end up getting x equals plus or minus the square root of 5. So that's about 2.24 if we graph these. So we have 2 zeros out here and here, negative 2.24. Again, 2.24. And then our horizontal asymptote, the degrees match this time. So the horizontal asymptote is going to be at 1 divided by 1, which is just 1. So we know that these are going to follow along here. And if we test out points on each of these regions, what we're going to see is if we plug in some values, save some time, we're going to find that we're actually going to follow below this asymptote here. These will be above, so we're going to look something like this here. And if we test some other points into this, it would look like so. So we have that sketch of our graph, right, using those big pieces. And our horizontal, or excuse me, our y-intercept is going to be at 0, 5/4 or 1.25, and that's where this piece right here is coming, is the 1.25. So we knew it was above. Okay, so that's just sketching the rationals, again, using the key points of the functions. Now, when we look then at some more graphs here, okay, if we look at graph A, they want us to analyze these graphs. So if we go back to Desmos and we look at graph A, notice here we have actually just a line when we graph this. And what we're seeing here is if we look at this as a table, at 0, it's actually undefined. If we were to try and graph this, there's a hole here in our graph, okay? And if we analyze this algebraically, what we can see here is actually this is factorable. There's a greatest common factor involved. And what we're noticing is really these would cancel out so that x equals 0, we have this canceling out. So what's really happening here is there's a hole at that value. So there's a hole at x equals 0. Now, on our graph, if we were to simplify this, right, if we duplicated this and simplified here, and we just talked about x plus 3 being our leftover piece, this would not have a hole involved with it. Right? If we made this into a table, we would see that at 0, 3, this would normally exist. So on our graph, if we were to graph this, we would put a hole here. We would put an open circle. But we know that that hole is occurring at 0, 3 because of that. Okay? So to find your holes, you plug 0 back into the simplified value to get what your y value of the hole would be. All right, let's look at another one. So again here, if we tried graphing the next one, so if we go to these first examples, and we looked here at the next graph, again, we're going to end up actually with a hole. Even though it looks like a line, we're going to end up with a hole if we actually look at the values of the table here. So if we duplicate this and look at the values of our table at x equals 2, there is a hole. And the reason being, again, if we look at actually factoring this, what we're going to see is that these cancel out, the numerator and the denominator, at the value of x equals 2. So this time our hole is going to be at 2 comma something. Now to figure out what the y value is, again, you would plug 2 back in here and see that at 2 comma 4 is where that hole would occur. So if we were able to see on here at 2, 4, they're not plotting this point because we know there's a hole there, right? It's skipping over that where it would normally with the rest of the values so have that. So 2 comma 4 would be the location of our hole. So to kind of expedite, now look at the graph here. Again, the hole in the next example in part C would occur at x equals 3. And again, in order to then find the value of the y at the hole, plug 3 in, we would have 5/7, and that would be the y value of our hole. And then last one as well. We see here the hole is going to be at -2. And then again, to figure out what that value is, we would have to plug -2 into the remaining pieces, and it would simplify to be 2/3, be the value at our hole. Okay. So again, anywhere this cancels out is going to be the location of your hole. And what vertical asymptotes and holes have in common is that they are discontinuities. Now, if something is a hole, it is not a vertical asymptote anymore. It's now the hole. So it no longer is going to count as a vertical asymptote. It would be considered a hole. So, but what they both would be considered is discontinuities. And again, that's where it's causing your denominator to be undefined, whether it's a vertical asymptote or a hole. So, moving on then to look at these and kind of in action. With these values here, if we look at the graph, in this case, if we factor this, what we're going to notice is that we end up with x plus 3 and x minus 2. And again, these are, in this case, vertical asymptotes, not holes, because they don't cancel out. So we would have vertical asymptotes at x equals -3 and x equals 2. So again, we would see that that denominator equaled 0. That's how we found that. Now, if they're asking us about left-hand side and right-hand side behavior of these graphs, we talked a little bit about this before, but what happens with these is we want to analyze as we approach our discontinuity from the left-hand side, what's going on with our graph, and as we approach our discontinuity from the right-hand side, what's going on with our graph, because sometimes the behaviors are different from one side or the other. So if we look at the first vertical asymptote, as we approach from the left-hand side, it's going to positive infinity. But as we approach this graph from the right-hand side, what we're noticing is that from the right-hand side of that vertical asymptote, it's going towards negative infinity. And that behavior is also going to be something we need to analyze for the other vertical asymptote as well. If x approaches -2 from the left, and as x approaches it from the right, are there different behaviors? Okay, like the other one. Well, if we look here, we have from the left-hand side of 2, so the left part, it's going to negative infinity, but the right-hand side is going to positive infinity. So this time, again, we have different end behaviors depending on what side you were analyzing. So again, the negative means your left-hand side, and the positive means your right-hand side approaching it. So understand looking at that. We'll talk more about analyzing it from different sides. All right, final piece of today is what we talked about actually back towards the beginning, is if you look at your graphs, and we talked about when the degrees are the same and when the degrees are different, when the degree of the denominator is bigger. But what happens when the degree of the numerator is bigger than by 1? Well, what we're going to see there is actually what is called a slant asymptote. And we're going to see this using information from number 9. So we notice here on our graph, here for number 9, if we add these together, what's happening, so what we see here is when we add them together, what's happening is we are getting a slant asymptote. So it's not horizontal and it's not anymore, it's a slant. And where that slant's actually occurring is when we have this line now. We see it's always with that first part here, so it's adding that rational. So if we look at the next example, 3x plus 1 over x, again, we have a slant, and where that slant is occurring is 3x, y equals 3x, would be that slant line, and then you'll see the same thing with this last one, another slant with y equals negative 2x plus 1 being the slant asymptote. Okay, so you see that in there. So if we go back to the notes and analyze here, each time, if we look at this, the line here that the slant is going to be occurring with, if we look at number 10, is the first piece here, which is y equals 2x plus 1, right? And it still has that vertical asymptote at x equals 0. Still see that in there. But we know the slant is this first piece. Now, what happens, however, when it's not written so pretty? It's written in the rational function version that we're used to seeing. Well, we know this, again, is going to have a slant asymptote because the degree of the numerator is bigger than the degree of the denominator by 1. So we know there's going to be a slant involved. But how do we get what the slant is when it's not so pretty? The answer is synthetic division. Okay, and the reason what we're going to do is we're going to use the vertical asymptote because we have a vertical asymptote at x equals negative 4. So what we're going to do is we're going to take that value of negative 4 and we're going to do synthetic division with the polynomial up top, 1, 3, negative 2. And if we bring this down, multiply, add down, multiply, add down, what we see here is this can be rewritten, this division, as x minus 1 plus 2 divided by x plus 4. So now we can see this first part here is going to be where our slant asymptote is occurring at y equals x minus 1. And again, we could check that by graphing the original here and graphing then that line to see did that in fact work out. Okay. All right. Thanks everyone for all your attention on this long lesson, and we'll definitely be working with all of these key pieces more in class.